Welcome friends. Now in this video we are going to talk about the merchant's second solution. Okay. The merchant's second solution. So we know that the merchant's first solution is actually giving the agreeable results for the synthetic rubbers or synthetic plastics, but it is not giving good results with the ferrous materials. So the main reason behind is that he has considered only the shear stress which is acting on the shear plane, but he has not considered the normal stress which is acting on the shear plane. So P.W. Bridgman give the relation for P.W. Bridgman gives the relationship for this tau S naught, or this tau S is equal to this tau S naught plus K times sigma, where tau S is, we know that this is the shear stress acting on the shear plane, and this K is a constant, this tau S naught is also the constant, and where the sigma is what? The normal stress acting on the shear plane. Okay, so we know that what is tau S? Tau S is equal to shear force divided by shear area, that is BT1 divided by sine phi, and sigma is the normal stress which is equal to FSN, normal to the shear stress, divided by shear area BT1 divided by sine phi. Okay, from this equation what we can write here? This tau S naught is equal to tau S minus this K times sigma, isn't it? So put the values of tau S. Tau S is what? It is Fs divided by BT1 divided by sine phi minus K times Fsn divided by this BT1 divided by sine phi. Okay, go on simplification, what we can get, let us see. So if I write like this tau SO is equal to, I will take this Fs divided by BT1 divided by sine phi common. So what is left with? 1 minus K times this Fsn divided by Fs, isn't it? So we know that from this merchant relationship between the forces, we know that this Fsn divided by Fs is equal to what? Sine of phi plus beta minus alpha divided by cos of phi plus beta minus alpha. So simply the ratio will be what? Sine divided by cos, this is tan of phi plus beta minus alpha. So put this value of this Fsn divided by Fs is nothing but what? That is tau S naught is equal to Fs divided by BT1 divided by sine phi into bracket 1 minus K times tan of phi plus beta minus alpha, isn't it? Now what is the shear stress then? The shear stress will be equal to tau SO into BT1 divided by sine phi into bracket 1 minus K times tan of phi plus beta minus alpha. Just I am simplifying this, isn't it? So this bracket complete. And we know that what is Fc divided by Fs for the cutting force and relation between cutting force and shear force. So it is cos of beta minus alpha divided by cos of phi plus beta minus alpha. So what is Fc? Is nothing but Fs into cos of beta minus alpha divided by cos of phi plus beta minus alpha. So again go on simplification. So what we'll get? See, we know that power is equal to what? Fc into Vc, isn't it? And what is Fc? Fc will be what? This is our Fc. Fs into this cos of beta minus alpha divided by cos of phi plus beta minus alpha into Vc, isn't it? But what is Fs? Fs is this value. So Fs is what? Tau s naught b t1 divided by sine of phi into bracket 1 minus k times tan of phi plus beta minus alpha. So this is Fs into this cos of beta minus alpha divided by cos of phi plus beta minus alpha. This is the Fc value into cutting speed Vc. You will get the power. Okay. So again you can see here the power is a function of work done is a function of what? The shear angle which is in the denominator. So again if I say that let x be equal to this denominator, which is, so let us multiply by this into the bracket. Okay, what we will get? That is, say, sine phi into cos of phi plus beta minus alpha, okay, minus k times sine of phi into sine of phi plus beta minus alpha. This tan is nothing but sine divided by cos of phi plus beta minus alpha into this cos of phi plus beta minus alpha. So this cos of phi plus beta minus alpha get cancels here. So what you left with? This sine phi into cos of phi plus beta minus alpha minus k times sine of phi into sine of phi plus beta minus alpha, isn't it? So this is our x. So to have this minimum power, it should be maximum. So differentiate this x with respect to phi to maximize this dx by d phi and equate to 0. So tell me this derivatives of this uv, u and v. So tell me. So first term sine phi into d dx of second term minus sine of phi plus beta minus alpha plus second term cos of phi plus beta minus alpha into d dx of first term, that is cos of phi, minus k times into bracket first term sine phi into d dx of second term cos of phi plus beta minus alpha plus second term sine of phi plus beta minus alpha into d dx of first term cos of phi and equate to 0. Okay, so what is this? This term I can write cos of phi into cos of phi plus beta minus alpha, isn't it? Minus sine phi into sine of phi plus beta minus alpha minus k times, what is this? Sine phi sine A into cos B plus cos A into sine A. What is this? This is sine of A plus B, that is sine of phi plus beta minus alpha is equal to 0. And what is this? Cos A cos B minus sine A sine B, that is cos of A plus B, cos of phi plus beta minus alpha minus k times sine of this phi plus phi 2 phi plus beta minus alpha equal to 0, isn't it? So this is cos of 2 phi plus beta minus alpha minus k times K times this sine of 2 phi plus beta minus alpha is equal to 0. So what is this? This cos of 2 phi plus beta minus alpha is equal to K. If this term goes at this side, it will be get plus, and this sign will come here, sine of 2 phi plus beta minus alpha, isn't it? So K will be what? Cos divided by sine. This is cot of 2 phi plus beta minus alpha. That is, this 2 phi plus beta minus alpha is equal to cot inverse of K, isn't it? And this cot inverse of K is nothing but, we are called it as 2 phi plus beta minus alpha is nothing but the machining constant. The Cm is known as the machining constant, which values depend upon which material you are going to have the machining or the material properties on that the Cm is going to depend on. Okay, so this is known as the Merchant's second solution, which will talk about the value of the energy as well as the shear stress, the induced shear stress, or this is also talk about the efficiency of energy utilization. Okay, now see, now this second solution was giving the good results as far as this theoretical first solution was giving. That is, first solution, if this is the phi and this is the phi beta minus alpha, so this was the Merchant's theory that we have seen, Merchant theory. Now this second solution holds good for the material, say copper, lead and mild steel. Copper, lead and mild steel have different lines but with the same slope. Okay, so it was quite agreeable results when you talk about the Merchant second solution with the ferrous materials. Okay, not like a synthetic plastics. So this theory actually this talk about the induced shear stress in the metal cutting as well as the efficiency of energy utilization. Okay, so see here, when this Cm value is equal to 90 degree, so whatever the induced shear stress into the cutting or into the material is equal to the ultimate shear strength of the material. That is, whatever the work done in the machining is equal to the minimum work done required to do the cutting. So in this case, what we can say that the efficiency of energy utilization is exactly, it is the 100%, isn't it? It is 100%. But when say Cm is less than 90 degree, so tau induced definitely less than the ultimate shear strength. So in this case, of course, machining is not going to happen. That is, we can say the work done is also less than the minimum work done. So of course, it is impossible for the machining. And here you are getting the efficiency of energy utilization greater than 100%, which is also not possible. But here, when the Cm, the machining constant, is greater than 90 degree, the induced shear stress is greater than the ultimate shear strength of the material, and the work done is greater than the minimum work done in the machining, and where the efficiency of energy utilization less than 100%. So this is the possible case. So this is the possible case. So from this we can also have the efficiency of energy utilization, we can calculate as 100 minus this 90 minus Cm value. Okay, so you will get efficiency of energy utilization in the metal cutting. So by the merchant's second solution. Okay, so see, now what are the assumptions actually the merchants have during its analysis. So let us list down this whatever the analysis, sorry, whatever the assumptions of the merchant. So if you write here the assumptions which are used in the merchant's theory, that the cutting edge of the tool, the cutting edge of the tool is straight and sharp. Cutting edge of the tool is straight and sharp. Second, the material is homogeneous. The material is homogeneous. Third, the material is rigid and plastic. The material is rigid and plastic. Fourth is the shear plane is extending to a narrow region, which can be considered as a thin straight line. Okay, so here, yes, we are assumed as the shear plane is as a thin straight line. Okay, so the cutting edge of the tool is straight and sharp, material is homogeneous, the material is rigid and plastics, and yes, the last one we can say the cutting is orthogonal. So these were the assumptions made by the merchant before giving this analysis for the forces in the metal cutting, and whatever we see, the work done, the criteria for the minimum work done, the criteria for the minimum power or criteria for the energy, and the efficiency of utilization. So we are having the Lee and Schaeffer theory and the Stabler theory. So students, after having this merchant first and second solution, there are the many researchers who have worked on this metal cutting to have the relationship between this, the shear angle phi, rake angle alpha, and the friction angle beta, or for they are also worked for the minimum energy criteria. Okay, so the next, after the merchant, the next scientists were the E.C. Lee and B.W. Schaeffer. They also put the theory for the metal cutting. Okay, E.C. Lee and B.W. Schaeffer, commonly known as Lee and Schaeffer theory. Lee and Schaeffer theory of metal cutting. So see here, again when they put forward this theory, only the difference between the merchant and this theory was, this theory, this Lee and Schaeffer theory was based upon the theory of plasticity. The assumptions they were having, that the slip line method for the analysis, or they have used the theory of plasticity for the analysis of this metal cutting. So what they have again assumed, that the material is perfectly rigid. The material is rigid and plastic, perfectly plastic. Okay, then they have approximated the shear plane is very thin line which is separating the workpiece and the tool. Okay, so there is existence of the shear plane as a very thin line which is separating the workpiece from the chip, or both of them, they are separating. So a thin shear plane separating the workpiece and chip. And of course the next assumption they have, that is there will be no any strain hardening. There will be no any strain hardening in the chip. Okay, so these are some assumptions that they have. So see, the important thing that you have to keep it in mind, the Lee and Sheffer theory, what it is based on, actually the theory of plasticity. That is a very important thing. You just keep it in mind. This is also known as the slip line theory or method they use for the analysis of metal cutting. And what the equation they got here, that please remember, very important, that is phi plus beta minus alpha is equal to pi by 4. Please remember, this is the equation or relation between these three angles: shear angle, friction angle and rake angle. Okay, that is, you can write it as phi plus beta minus alpha is equal to 45 degree. And if you see, if you plot the results, experimental results, so they are always matching with the Merchant's theory, or the trend which have we observed in the Merchant's second solution, that the theory is quite agreeable for the say copper, lead and mild steel. This was the basic first solution. Okay, first Merchant and Ernst and Merchant theory. This was the Merchant theory. Okay, and here are the experimental results for the second solution, that is, this is for copper, lead and this is mild steel. So they were having the agreeable results, having the different lines but the same slopes. So like this trend of phi versus beta minus alpha we get observed into the Lee and Sheffer theory also. So not much deviation from the Merchant, so it is not so appreciated. After that, again one more scientist came, that is and he put theory, that is the Stabler. Okay, so there is a Stabler theory. Again, what Stabler says, that is phi plus beta minus alpha by 2 is equal to 45 degree. So this is a Stabler equation. Again, quite same results as per the if you compare it to the Merchant's theory. So see, simply we can say these two theories, many theories come forward after the Merchant theory, but all these theories are, again, it's quite failed theories, because see the trends, we are not getting too much deviation from the Merchant what he put forward. So that's why we can say these are the failed theories. So only we are having in the metal cutting analysis, we are using still now the Merchant's theory. Please remember, if in the question it is they are intentionally given that use Lee and Sheffer theory or Stabler theory, then and then only you can go for this relation, that is phi plus beta minus alpha is 45. This is the Lee and Sheffer theory, and phi plus beta minus alpha by 2 is equal to 45 degree, it is Stabler theory. Okay, but if given in the question, the maximum times they will give you use the Merchant's theory. Merchant theory क्या बोलती है? This 2 phi plus beta minus alpha is equal to 90 degree, or the second solution says it is machining constant Cm. 90 instead of 90, it is coming as we have proved this. It is Cm, that is machining constant, which is depend upon the material properties or material to be cut or to be used in the machining. Okay, please keep it in mind. Thank you.